Good morning and welcome back. We were looking into some of the, rather revisiting some of the basic network theorems. We'll do the same thing in this class before we go back to dealing with nonlinear two-poles. So most of you, yes, in the last class told that you are aware of what Thevenin's and Norton's theorem is. So I'll run through it quickly. But before I run through it, tell me what do you understand when I say Thevenin's theorem? So let's say I have a network. And maybe I have diodes, MOSFETs, and everything. Then tell me what Thevenin's theorem is. Okay, if the circuit is linear and we have active steady state. Okay, fine. So let's revisit that. So which essentially means that I cannot use diode, right? You cannot use diode. Can I use a control source? Let's say I have a VCVS or VCCS or CCVS. There are 4 types of control sources that we know, right? Voltage control current source, current control current source, voltage control voltage source. Depends within that. I can extend the boundary of the box, right? I didn't understand. A control source always depends on something else. When you say device, do you mean that? Okay, maybe. I mean, let me go through it, then we can talk about it. Okay. So, as you said that if you have nonlinear elements, you cannot use Thevenin's theorem. Are you aware why? I also have to doubt. There, some component, there's some pi here, with I is the current into the. Can you still apply Thevenin's theorem? You can apply Thevenin's theorem everywhere, as long as it is linear. Okay, and even the steady state thing is not particularly valid. We'll see why. Okay, so we normally, I mean, in the questions that we attack, we say steady state because it's easier to solve. But Thevenin's theorem doesn't really matter whether circuit is in steady state or not, as long as you can. Okay, let's go through the proof. Maybe that will help clarify things. So let's assume we have this network. You have voltage sources and current sources also inside. So what Thevenin's theorem says is that if you have this port, right? If you have this port and maybe you have some impedance connected to it, maybe RL, it can be ZL, any type of ZL, it doesn't really matter. So what Thevenin's theorem says is essentially the voltage across this VL, and if I denote this current as IL, so I can figure out this voltage obviously by solving the KVL, KCL of the entire network. Alternatively, what I can do an experiment, rather 2 experiments. In one experiment, I will open this RL. In one experiment, I'll open this RL, and this network remains as is. Let me take out these voltage current sources because that will help make the point. Assume this voltage current, I mean, I am taking out the voltage and current sources. Nothing has changed, but essentially I've taken it out to make a point. So this VL will be the sum of 2 voltages obtained in the following manner. So in experiment 1, we'll remove that load and we'll observe the voltage here, VOC. OC means open circuit, and we will take a note of it. And in the second experiment, we will try to figure out
what is the impedance looking into the port, right? What is the open circuit impedance or the impedance looking into the port? And when you are trying to find out the impedance, what do you do with the sources?
Sure.
You have to de-energize them, right? You have to desensitize them, which means all the voltage sources will be nulled and all the current sources will be open, right? So all that, mind you, these are all independent voltage sources and current sources that are being nulled and opened. If there are dependent current sources inside, they remain as is, right? So all the independent current sources are open and voltage sources are not. And we are trying to figure out what is the output impedance. And if I give you a network, how do you figure out an output impedance experimentally? What will you do in the lab? If I ask you, I give you a network and ask you to find out the impedance, what will you do?
Short that.
And you are saying something?
Short.
No, you are in lab. You are not calculating. You are experimenting. What will you do?
We'll connect and there.
Okay.
We'll calculate the.
So first, okay, fine. So you will short it, then you will connect an ammeter. But there is no source inside. Why will current flow? No, right? When you are trying to figure out the impedance, you are null the sources.
So that is theoretically the answer.
No. Yes. Yeah, multimeter gives you the art, right? But multimeter operates in the principle. Right? I'm asking for the principle. Let's say you have voltage current sources available in the lab. So how will you figure out an impedance? What you said initially was correct, right? So you'll have to essentially apply a voltage source here and put maybe an ammeter here and figure out what is the current going through it. You know the voltage that you have applied and you find out the current, put it in a CSV format, divide. Right? So essentially that's how you'll get an impedance.
But there are sources inside the network.
There are no sources inside the network. I have nulled it. Right? So all the current sources have been opened and the voltage sources have been okay. So basically, by the way, this is exactly what we will do. I mean, later on in the course, we will be needed to figure out what is the resistance, impedance, admittance of a network. Initially, we will be putting voltage sources, current sources, and figuring it out. Later on, I'll assume that you are comfortable enough to look at the circuit and figure out what it is. But essentially, the practice that we'll be doing is we'll be adding a test voltage source here. Let me call it a test voltage, V test. And it not be a DC, it can be an incremental source, it can be an AC source, depends on the situation. And we will be finding out the current that is flowing in I test. And V test over I test will be your impedance, right? So this essentially will be the, maybe 1/3 of the course will go in finding impedances. So it's critical. Yeah. Yeah, any voltage source. Is the impedance. Why is that right? Okay. He is asking how. Okay. So when I am saying that I can find how to find out an impedance, which means that I am implying there is an impedance, right? So if you agree with the fact that there is an impedance, let's say it's called Z, then I can replace whatever looking in with an element which is Z, right? So now the question is, how do I find Z experimentally? He said you can put a multimeter. Experimentally, yes. Right? So essentially, when you put a multimeter does this for you. It has an internal voltage source. You put a voltage source and you figure out what the current, do the division and show you a number.
We are doing this for a particular frequency.
In a multimeter, it will show you for a specific point, but it need not be for a particular frequency. When you do the calculation, this Z can be Z omega, right? It can have a frequency dependent component. If you do the experiment in the lab, you will be setting this V test at a particular frequency and you'll be noting, let's say you set the v-test at omega naught, and you figured out what is I at omega naught. That ratio gives you a number. The number will be complex, right? It will have a real part, it will have a complex part. That will be the impedance at omega naught. Then you change the frequency, take another measurement. Then you change the frequency, take another measurement, right? So that will, essentially you will get Z of omega across frequency. Okay. Okay, fine. So let's stick to resistive, non-imaginary components. So, and we did this experiment and we figured out what is the open circuit voltage, open circuit resistance. So now what does Thevenin's theorem tell us? Thevenin's theorem essentially tells us that I need not know what is going on inside the box as long as I know what is VOC and ROC. I can replace this network with VOC, ROC, and these are my 2 ports, right? So this, let's say 1. So these are my ports. And if I have an RL, I can as well connect the RL here. And the voltage that will develop across RL will be equal to VL. So this voltage, right, VRL, which is equal to VOC times RL by ROC plus RL, will be equal to the VL that I would have gotten here. This is the statement of Thevenin's theorem. We all know this. Now the question is how do we come about? How did anybody come about with this weird looking stuff, right? I mean, this seems very simple. If any network, any linear network you take, you do 2 sets of experiments, you don't have to know anything else about the network. So the derivation of the theorem is also quite simple, but let's go through it once. Let me just say this is IL. Now note that this circuit I can replace this network is identical. Now using substitution theorem, I can replace this resistor, right? I can replace this resistor with a current source which is carrying the current that is flowing through the resistor, right? That essentially is the substitution theorem, and nothing else in the circuit will change. Do you agree? Right? I am just invoking substitution theorem, which essentially means that I am replacing this with a current source of value VL over RL, because the current flowing through this was VL over RL. Fine. Do you agree? I don't see, very skeptic. So let me ask somebody, why don't you not agree? Why do you not agree?
So what is the question?
The question is, can I replace this resistance with this current source of value VL over RL? I've used a theorem, right? I have used substitution theorem. And what is substitution theorem? If I take you back one class, if I have an element, if I know the voltages and the currents through it, I can replace that element with a voltage source, which is equivalent to the voltage drop, or a current source, which is equivalent to the current going through it, and nothing in the rest of the circuit changes, right? And we proved it. Okay, so I'm essentially invoking substitution theorem. And substitution theorem is valid for nonlinear circuits also. So linearity hasn't yet been imposed. Okay, so what I have done till now is generic. I haven't till now imposed linearity. Okay. So now what I'll do, I'll impose linearity. What I'll say is that this voltage VL, right? This voltage VL can be obtained by principles of superposition, right? So where I say that if the network inside is linear, I can find VL by superposition where the two superposed networks are the following. I have this linear network, and I will retain the sources here. But note that since this is a current source, I will not use that current source in the calculation in the first circuit. So essentially, I will desensitize that current source and figure out what is my output voltage, right? Let me call it VO1. And in second experiment, I will desensitize the sources that were there in the network. That is, I will short the voltage sources and I will open the current sources, and we'll use this current source that I got in the previous step. And let me call this V02. And what superposition is telling us is that VL will be equal to V01 plus V02. This is superposition. Okay. So note that this step is not allowed if a circuit is nonlinear. Right. So this is the step where I have imposed linearity. So now this voltage V01 by definition is the open circuit voltage, right? You have done an experiment where you have opened the load and you have figured out what is the output voltage, right? So V01 is open circuit voltage. What is V02? If this impedance looking in is our open circuit, what will be V02?
R open circuit minus R open circuit.
Exactly, right? So you have a current source which is dragging current out of an impedance of value ROC, right? So this is equivalent to saying that I can replace, this is equivalent to saying you have ROC and this is VO2, right? So VO2 naturally becomes minus ROC times VL by RL. Okay. So by definition of superposition, your VL becomes VOC minus ROC VL by RL, which means so this is what Thevenin's theorem is. So why is Thevenin's theorem powerful? It's powerful because normally when you buy a network, right? I mean, you as a customer, think of you yourself as a customer. You go and buy a network or any circuit, and you are trying to figure out how the circuit will respond to a load that you attach, right? So one way to do it is attach a load and figure and see how it responds, attach another load and see how it responds. Another way to do it is you can ask the seller or ask the vendor that what is the Thevenin equivalent of your circuit, right? The Thevenin equivalent is not particularly, it's not dependent on the load that you have attached. It's an open circuit model. So when you have an open circuit model, then you can simply use the Thevenin equivalent. That is, Thevenin equivalent is telling you that if you have VOC and if you have ROC, then you can attach any load to it and figure out what will be the impedance, what will be the current through the load and the voltage across the load. You don't need any a priori information of what is inside the circuit. Okay. And from the perspective of a designer, it also makes life simpler for you. If you, let's say, you want to sell a product, you want to attach that whatever you have designed to any particular load, you don't have to go and tell the seller or your friend who is using your circuit or whoever. The information of how the circuit is made is unnecessary. All you need is that open circuit voltage and open circuit or other output impedance, right? And these two information makes life easy. Again, layer of abstraction, right? You make layers of abstraction are used to make life simple. And this is one example of that. Now, coming back to his point, anywhere did I used all caps VL and constant voltage sources, constant current sources. But do you think this is applicable if all these voltage and current sources are time varying? Did I take in any of these steps, did I assume that if things are changing with time, it will not be valid? No, right? So which means that even if I have a AC voltage source or an AC current source, things will be okay. And why AC doesn't necessarily need to be AC. It can change in any form as long as I ensure that linearity is imposed. There is no other condition, no other constraint on Thevenin theorem. Yes.
Sir, while doing superposition, we on the output side we must open the current source, and then again on the input side we did the procedure of opening and shorting the voltage. So why did we not simultaneously open the current sources and then in the second step while maintaining the current sources short the voltage source?
Okay, I mean, you can, so you can do, there is nothing stops you from doing that. But I mean, just like any theorem, you have to prove, you have to follow a certain steps, which makes life easy, right? So this is essentially that.
So sir, would it be getting us the same answer or?
It will give you the same answer. I mean, if you do the experiment, you will get the same answer. But I didn't do that because, I mean, then I have to find out what will the impedance looking in here, right? Right. So that was not the goal. So I didn't take that path. Okay. So any questions regarding these steps? Yes. Okay. Sure. Okay. Fine. So as long as you are satisfied, I'll not prove the Norton's theorem. Norton's equivalent is what? You can just tell me the statement. Right. So essentially, instead of getting into this open circuit voltage, I will replace it with a short circuit current source. I mean, how do I experimentally find? I short the output and figure out what is the current flowing through it. We call it short circuit current. And open circuit resistance, anyways, we know. So we replace this VOC ROC with a short circuit current source and a ROC in parallel to it, right? So essentially, the statement essentially is you can replace that circuit on top with a current source and ROC, and this becomes your ports, and you can attach whatever RL you want, right? And this current source ISC, in terms of Thevenin's, in terms of the Thevenin voltages and currents, what resistances, what will be the value of this current source? Yeah, so essentially this will be VOC by ROC. Right, so we'll be using this, Norton's theorem and Thevenin's theorem a lot in the course. So if you have slight jitters about it, I would say come in, go ahead and go back and do some of the assignments on this, right? Okay, so now since let me talk about one more thing. This current transformation that we did, right? So, or source transformation. I mean, you said that this is equivalent to VOC, ROC, RL. These two are equivalent, right? So now my question is, why are these two equivalent? In essence, what I'm asking is, let's assume you have a source, let's say the in, and you have Rn or Rs. And you have a nonlinear network. Okay. So can I replace this input contraption with a voltage, a current source and a voltage source? Can I do this? The question is, why can I do this? Okay. So what is pointing out is that if this resistance, instead of a resistance, if I had a nonlinear element whose current voltage relationship is related in a nonlinear fashion, then I couldn't have done this, right? If this is some E, then I couldn't have done this, right? So again, the reason is simple. Let me show it why. So let's assume you have done this on you have fiddled with the circuit on the left, and you have figured out that this voltage is V1. Right? The voltage difference between these two nodes are V1. Okay, so the current that is flowing in through RS is V in minus V1 by RS. Okay, so what I'll do is, so I know that V in minus, this is equivalent to V in by RS minus V1 by RS. So I will replace this current that is going into it, that the current that is going into it with, so this is my f of V. The current that is going into it is V in by RS minus V1 by RS. This I know, which means that I will arrange this current in this manner. I will replace this input source by V in by RS, and I will take a current out, which is equivalent to V1 by RS. And I will connect it like this. No harm done, right? The network, that nonlinear network, is still seeing the same current that it was seeing originally. So by superposition, by substitution, this voltage will still be V1, right? I haven't changed the current that is flowing into the network. So now if you buy this, now note that what has happened. This voltage is V1. The current through this source is V1 over RS. So this source, even though I have replaced it with a independent source, this is kind of a dependent source, right? It's responding to the voltage across its terminal. The current that is flowing, that it is dragging out, is proportional to 1 over RS, right? So what is an element that pushes in current or drags out current, which is proportional to the voltage across it? It's a resistor, right? The current that I am getting out from V1 is equal to V1 by RS, which means this is a resistor. A resistor essentially is a dependent source. The dependency is between voltage and currents, right? I mean, it's not a source. Don't hold me legally to it. But what I'm trying to get at here is that there are dependencies. So you can, I mean, this source, the way I have connected it here, seems like the current that I am pulling out is proportional to the voltage, which means I can replace this source as with a resistor of value which is equal to the dependency, right? So which means that I can replace this with a resistor. which is RS. And this value will be V in by RS, and nothing will change. This will still be V1. So hence you can transform the sources from voltage source RS in series to a current source of V in by RS and RS in parallel. Now note that, well, I mean, what couldn't I have done if RS, instead of RS, I had a nonlinear element? Which step was not possible? The step that wouldn't have been possible is I couldn't have expressed the current that is flowing in with this expression. It would have been some F of this current would have been some F of, or maybe it shouldn't be F, it should be some other nonlinearity because I've used F. So let's call it G of V in minus V1. The current that would have flown in would have been this, right? If the element was nonlinear, which means that I couldn't have expressed the current through this, which means I couldn't have replaced, I couldn't have done this step. This step wouldn't have been possible, which means I couldn't have replaced, right? So this is where your source transformation would have broken. Yes.
Suppose if there is another linear element, would be still.
Yeah, exactly, right. So all you need to ensure, all you need to satisfy is this condition. This current that is going in is V in minus V1 proportional to V in minus V1. That's all, right? I didn't understand which. Oh, sorry. Yeah. Okay. So the point that I was trying to make was, yeah, thank you. So this was factually incorrect, right? So what was I? Where was I when this? I was trying to make the point that this is equivalent to this. And I was trying to say why it is equivalent, right? So yeah, so obviously this resistance has to be there, otherwise it wouldn't have. Okay. Yes.
So, sir, is it safe to say that in case of non-linearity, the principle of
Yeah, in superposition is only true for linear circuits, right? Superposition is not true for nonlinear circuits, and essentially that is why wherever you are using superposition, you cannot use nonlinear. I mean, you cannot have nonlinear circuits, right? But having said that, now that you know how to, I mean, if I use a nonlinear element and I know how to linearize it in the incremental model, they are all linear. So let's say I replace this RS with a diode. So in the truest sense, in the full nonlinear sense, I cannot do this. But in the incremental sense, can I do this? I can do this. I'll be replacing the diode with its resistance, and the current voltage relationship between the voltage and the, I mean, across the diode and through the diode is essentially linear. So I can do this step. If I had a diode instead of RS, the capital I, capital V replacement wouldn't have been done, but the small I, small v replacement would have been done, right? The incremental replacements I could have done. Okay. So that is why you see that going forward, we'll be using nonlinear elements everywhere, but we'll be still using these principles. But these principles will be used in the incremental domain, not in the full IV domain. Okay. Okay, good. So one last theorem, very powerful theorem I wanted to touch upon, that is Tellegen's theorem. You have heard of Tellegen's theorem? Okay, what is Tellegen's theorem? So let me sketch a generic network. And let's call these voltages names anything, right? So let's say this is the kth branch, and the voltage across it is Vk, and the current through it is Ik. And let's say I have another network, and the only commonality between this network and the network that I am sketching is that they have the same graph, which means that this can be one element E1, this can be another element E2, this can be a voltage source, this can be a current source. Whereas in this case, this can be an element E5, this can be E9, this can be a voltage source, this can be a current source, this can be another element capacitor. Doesn't matter. It can be a completely different circuit. But only property is that both of them have the same graph, which means that the branches are still I can correlate the branches. So if this is the kth branch on the left circuit, this is still the kth branch on the right circuit. But the voltage across it will definitely not be equal to Vk. I call it Vk hat. And the current through it will definitely not be equal to Ik. I call this Ik hat. And note that this can be at any different time also. The circuit on the left, I might be observing at time T1, circuit on the right, I can be observing at time T2. Doesn't matter. So under these conditions, there is a very powerful theorem. We call it, yes. These two are totally uncorrelated circuits. Only commonality is they have the same graph. Right? As general as it can get. Okay. So what is the statement of Tellegen's theorem now?
Summation of T I j is equal to 0.
Okay, so Tellegen's theorem essentially says that summation of Vk, Ik over all branches is equal to 0. So this is also true for the circuit on the right. That is Vk hat, Ik hat. Does it say anything else? Right. So, and also this is also equal to Vk times Ik hat. This is also equal to Vk hat times Ik. So all of these are independently 0. Now, these first two, it's simple. I mean, this essentially is that it's an isolated network. No power is going in, no power is coming out. Summation of all power dissipated and generated is equal to 0. Right? So this is simple. What do you mean by hat? Hatted network is the next network on the right. Right? Okay, so you can call it cap, hat, doesn't matter. So yeah, so what was that? Okay, yeah. So the first two conditions, that is this and this, are quite straightforward. You sum up all the power dissipated and generated in the network, add up to 0, no problem. But these two are not so obvious. So let me quickly run you through why this is as is. Okay, so let's mark some currents and voltages, otherwise it will become too generic. So let me call this I1, I2, sorry, I1 hat. Call this I2, this is I2 hat. I3 hat. Okay, so what I'll do is, again, I'll do the same thing that I have done a couple of times before. I will add 0 currents to all nodes. Right? I can add 0 currents in n number of ways, but in this case, the 0 current of what I'll do is I'll take the I'll add the 0 currents on the circuit on the left, and the way I will do it is the following. So I will add Ik hat here. Similarly, I'll add I3 hat here. Similarly, I will add I1 hat, I2 hat, and this is I4 hat maybe. Okay. So note that why am I saying that doing this will be adding zero current is because if I look at this node, right? If I look at this node, what is this node telling you? It's essentially telling you I1 hat plus IK hat equal to 0. Right? Sorry, I1 hat equal to IK hat if the direction is the other way around. And this node is telling you that IK hat plus I1 hat, IK hat equal to I1 hat plus I2 hat. So essentially, I have the KCL at each node on the circuit on the right satisfies that current going in is equal to 0. I have just superimposed that same KCL condition on the circuit on the left by adding up the currents in the direction it was in the circuit on the right. Okay. So essentially, if you are convinced that no, I have not essentially added any, I have added zero current at each node by doing all these things, then I can simply do the power conservation in the network of the new network, and the power conservation in the new network will be okay. So let's see where is the removal. So do you agree with the fact that on the circuit on the right, I1 hat is equal to IK hat if I do a KCL at this node? So which means that I1 hat minus IK hat equal to 0, right? So now note this node, I have pushed in current I1 hat and I have taken out current IK hat, which means nothing has gone inside.
So basically it turns out to be the same thing.
Exactly, right? Right? So exactly. So I have to copy the entire current with time information also. If there is a time information associated with this current, I have to do the same thing, right? So
Sir,
yes.
please explain that part.
Okay. So the part that I just commented on. So what is your question? How come I have added zero current?
Yes.
Okay.
The same.
Okay. Fine. So let's take any node. Let's take any other node. Let's take this node. So what does the KCL at this node tell you? This tells you that IK hat is equal to I2 hat plus I3 hat. Correct? So now look at the corresponding node here. So what is the current what is the remnant current that is going in to any of these elements? Let's say the current that is going into the element on the right. No, right? So because see, how much what is the total current that I have added at this node? The total current that I have added is IK hat minus I3 hat minus I2 hat. Right? Essentially, this is equal to 0 because KCL was satisfied for these values of hatted currents on the network on the right.
For the other network, by having the KCL in the other network, we are essentially putting that.
Correct. Right? Exactly. So note that till now, I haven't, imposed any condition on whether circuit has to be linear, non-linear, active, passive, time dependent, time variant, nothing. Right? So only KCL has been applied, and KCL I can apply for any network. Okay. So if you are satisfied with this, this is the key step. Are you satisfied with this, or do you want me to spend some more time on this? Okay. So if you are satisfied with this, then the next step is simple. I do the power conservation on the circuit on the left, modified circuit on the left. So what do I get? So if I do a power conservation, now let me concentrate on any one of the branches and I will add them up. So let's concentrate on the kth branch. What is the kth branch telling us? The new kth branch now has the same good old voltage Vk, because I didn't add any current, so voltage shouldn't change. The current through this is now, this was original IK, and I have ik hat. Right? So now this is my new kth branch. Okay. So similarly, we'll have a parallel combination of these new current sources for all the branches. So I will add up the power between these two, each of those nodes, each of those terminals, power dissipated between each of those terminals. So what will the new equation? New condition will be summation of Vk times Ik plus Ik hat over all k will be equal to 0. This is for power conservation in the new network. Now note that Vk times Ik summation over all k was 0 anyways, because the original network had this condition, right? Which essentially means that, so since Vk times Ik over all k was 0 in the original network, this implies the summation of Vk times Ik hat over all k will be equal to 0. Yes. Okay, so okay, fine. Okay, so this is so what will be the current that is flowing in?
Sir, I was not telling that we can write this AK minus IK. I was telling that if this IK had current, so what essentially is happening is, so IK current is from this source, it is going into the other two extra sources that we have added.
Right.
Correct. So it is never entering any of the elements that was previously in the circuit one. It is going from source to source.
Totally agree, right? So, but now put a black box, or rather I should put a different colored box. Okay, so I put this box across each of these elements, right? So now I observe the current going into it, those boxes, and the voltage across those boxes. Okay, so then I can write this. So the current that is going in is Ik plus Ik hat. Similarly, the current that is coming out is the same. The voltage across the terminals is Vk. So I can write this.
Black box becoming the new element.
Correct. Exactly. The black boxes are becoming the new element in the jumbled up network, right? Okay. So now, which essentially means that you get this condition of Vk times Ik hat equal to 0, summation over all. Now note that this Vk is a voltage in some network, and Ik hat is a current in some completely different network. The only commonality is the same graph. Again, at the cost of repeating myself, it can be linear, non-linear, time variant, time invariant, observed at different times, doesn't matter. This is still true. One of the most powerful theorems in network. I'm sure you know this, reciprocity. Right? The proof. Do you know the proof of reciprocity? True, but in this context, when I say in terms of circuit, what is reciprocity? You can have, if you have a, let's say, 2-port network or an 8-port network, you apply voltage at one source, observe the current in one source, other terminal, and you reverse, the ratio remains the same essentially, right? That's what reciprocity is. The proof of reciprocity in these conditions is it starts with Tellegen's. Without Tellegen's, there is no reciprocity. Okay, so I was planning to cover reciprocity today, but we are out of time. So we'll cover it tomorrow. We have a class tomorrow. So we'll cover it tomorrow and then go back to where we left off, right? In the sense that go back to incremental 2-port networks. Okay. Okay, we have 1 minute. If you have any questions right now, we can address, or we can address it outside. Yes.
When you are studying Thevenin's theorem,